Okay, so it's my great pleasure today to invite and introduce Ellie Pavlick for the last of our 2024 talks in our CCCM Cognitive Science of Generative AI series. Ellie, as we were just discussing before we started here, started out with an undergraduate from Johns Hopkins in economics and saxophone before moving on to a PhD at Penn in computer and information science, and is now a professor in computer science and linguistics at Brown, where she leads the Lunar Lab, which is, I think, a really cool name, language and understanding and representation, and is also a research scientist at DeepMind. And I'm particularly pleased that Ellie has agreed to speak to us today because she's super busy. And also, she's really one of the first people in this arena that took large language models seriously as a cognitive scientist and did sort of serious, rigorous work on trying to understand their representations. So I can't think of anyone better to close out the year than Ellie. So over to you then.
Thank you so much. And yeah, thanks for organizing this series. And the cognitive science of generative AI is something that I hope probably over the next years will become like a fairly real discipline, right? Like I think there's just so much here. So um okay, so I want to give a talk that's kind of on two newer projects, so two unpublished projects, because I tend to find it more fun to talk about unpublished work. But also as a result, it's something of a grab bag, right? I'm playing around with stuff. So I love to have plenty of discussion. And this is a small group, so it can be informal and discussed. I've given a version of this talk once before, and so I don't have like a really great intro into it. So I think kind of the kind of conversation that I think a lot of the work we're talking about here, especially in the cognitive science of Gen AI broadly, and a lot of the work we're doing in my lab, like the conversation this contributes to is definitely this old one where there's kind of been traditionally viewed this kind of competition between neural network models and what we would call something like cognitive architectures as models of cognition, where we're assuming that the neural network models they have sub-symbolic representations. They're learning things from statistical associations, and these cognitive architectures have more formal compositional structured representations of the phone volition variety. Um, increasingly in modern times, I would say that there's a lot more nuance to this discussion, and a lot of people who are fairly informed say, well, no, cognition is really modeled as some more hybrid of this with, neurally components taking over some pieces and symbolic components taking over other pieces. I'll admit I can't quite figure out exactly where the work we're doing in my lab and probably broadly within this group, like how exactly it fits into this picture. And it's something I struggle with. So I've tried to make an intro that takes a stance on this. And no matter how I give it, I'm like, no, that doesn't quite reflect how I believe. So I'm not really going to take a stance. It could be something we talk about more in the discussion. The kind of issue is that the current models we have, especially large language models, are doing stuff that this debate has tended to say is the job of the symbolic side. So stuff like compositional reasoning to some extent, logical language, I mean, just language by itself, right? So even when we've talked about hybrid architectures in the past, we've said like, well, the neural nets can do stuff like maybe visual perception, but language would go to these symbolic components. And that's on a superficial level, not what's happening right now. So the very interesting question to me is like, what is happening inside the language model that is allowing it to do this? And then if we knew that, then trying to figure out where it fits into this picture, like is the neural network implementing a symbolic component? Has it found an alternative solution to doing this? And what should that tell us about these things generally? So right now, like I said, this is kind of a really hand wavy intro because I don't really know what the thesis is. We're basically still collecting evidence, and I like to lead into a talk with some kind of thesis, and I don't really have that. But it's something that fits somewhere on this picture. And so instead, I want to talk about kind of two papers that I think, like to me, to the extent that there's a thesis, it's like, maybe the neural network is something like a complete model of cognition. Maybe it's handling both the traditionally neural side and the symbolic side. And there's kind of two papers that are pointing towards this. So one is some work I've been doing with my postdoc Jake and Michael Frank, who's a neuroscientist, on in-context learning. And what we're looking at there, and the claim there is that the neural networks, because they have both in context or in weights learning and what's called in context learning, they can do both this kind of low-level neurally stuff as well as this higher level symbolic stuff. And they can get these nice trade-offs that we would expect on the human side. So I'll talk about that paper first. That's closer to a mechanistic paper. And then the second claim is just looking at how well large language models perform at modeling tasks that have really traditionally been used to advocate for the need for this high level symbolic structure, so particularly a concept learning task. And in that case, we're finding that the language models are actually a better fit for the human data than something like a probabilistic Bayesian model. And so I think that also, really, I guess, demands attention in terms of what we're saying is like the job of the neural network versus other things. So I kind of like to put these two papers together because I feel like somewhere in here there's kind of a shape of what the model is, but it's not quite there. All right, so I'll start with the first paper. Okay, so like I said, this is work with my colleagues in neuroscience. So human learning is not one thing. This is a thinly veiled attempt to get a video of my daughter Sammy in because she's very cute. But here you can see her trying to learn how to use a cup, and she's at this point just chewing on it, but then she starts banging it and flipping it around. And this is like a common part of the learning process. What we think of as kind of almost like the reinforcement learning process, where you just have many, many, many interactions with cups and many failed interactions with cups before she reliably learns how to use a cup. And then you can contrast with this, the other kind of what we might call learning or maybe reasoning that humans do, which is like if I walk into some kitchen I've never been in before and you ask me to put a cup away, I could very quickly like look at this shelf and figure out where the cup goes. And this can happen on the fly almost instantaneously, right? Based on kind of very quick pattern recognition and reasoning. And these are very different processes and can rely on very different mechanisms. So we typically think of these kind of dual, like this duality to human learning. And I'm using the word learning here, which people have pushed back, and I agree. Learning is maybe not the best word for both of these, but I'm going to use that because that's what's kind of consistent with the terminology that's being used in AI right now. So we have, on the one hand, we have learning that's slow and it's incremental and it's highly habitual. This is something like learning how to drink out of a cup, learning how to ride a bike, learning how to type on a keyboard, learning how to play piano. It's slow to learn, but then once it's learned, it's very highly retained, and it can be hard to change. Actually, this makes the music lead in pretty appropriate. Where I was saying that I played saxophone for many, many, many years, studied in college, and now it is like instantaneous. I know where to put my fingers in order to play music. Like that is like baked into me, right? Even though I sound terrible now, but it's highly retained, right? And this is in contrast to what we would call this this other process, which is, it's much faster. It's like figuring out where a cup goes within this kitchen. But it's probably rule-based and compositional, and it's not going to be retained. Like, much later, I would have to reason anew. If 5 years later I come back to the same kitchen, I'm not going to remember where this cup went, but I could figure out again on the fly, right? And so traditionally, these have been kind of, they get talked about as though humans are capable of doing both of these things, and they rely on different systems. And when we think about neural networks, the traditional work on neural networks kind of assumes that neural networks are a model of the blue one, right? The slow, incremental, habitual learning. And so when we think about neural networks in that way, as doing this slow, incremental updates on their weights over something like gradient descent, they show the kinds of properties we would expect from, these kind of systems. So they struggle with things like systematic generalization, or compositionality. I'm just pointing out some work that I've liked that illustrate this, but there are a lot of arguments to this effect that show, for example, if you train a model on some kind of simple semantic parsing test, it doesn't generalize well compositionally to held out examples. And these are neural network models that are trained from scratch on these tasks, right? But then this seems to create some kind of contradiction with the kind of work that's coming out with large language models now. So this is an example from Taylor Webb's work on analogy that shows if you give models, these large language models, some examples of these kind of analogy problems or compositional problems in context, they seem to be able to understand what's going on in the task and generalize compositionally in that way. And so this creates this, apparent conflict where we're saying we have some studies that the kind of, you know, the tweet version is neural networks don't generalize compositionally, and then have other studies that are saying the exact opposite. And it would seem that these are in contradiction with each other. I think what we're leaning into in this work is that they're really not in contradiction because um, these large language models really have these two systems happening kind of in superposition of one another. So they have their in context, or they have their in weights learning, the kind of traditional, the weights that are updated from gradient descent, but then they're also able to what we call learn in context in the activations, which is recognize patterns and complete those patterns without making updates to their weights. And so these things are obviously intimately connected, but you can kind of think of them as like two faces of a coin or something, right? They kind of have different properties, and they can be seen as two different systems. So you have the in weights updates that gives rise to this in context learning. And then or into these patterns of activations. Those patterns of activations yield some type of behavior, which results in a reward or a loss, and that comes back and updates the weights. But then after sufficient training, you might have the activation space capable of recognizing patterns and completing those patterns without requiring changing the weights. And this is what we call this kind of in-context learning. And when that happens, you'll stop getting losses, you'll stop updating the weights, and so you get this kind of breaking out of the two systems. And so you end up with this world where this kind of maps onto that picture I had earlier. So the in weights updates are slow and incremental, and they're highly retained. And this once you've got this stuff that's being learned in context, it's fast and flexible because it adapts differently to different inputs, but it's not retained because if you're doing this well, you're no longer making errors and you're no longer getting updates to your weights. And so the proposal in this paper is to basically view the neural network as having two systems here, the in-weight system and the in-context system, and saying that this can unify some of the results that we see on the human side, which have been used to support this argument about dual systems. So these are the kind of the two systems that we're talking about. I at some points have called it system one and system two, and also have been told that that's confusing and overloading some terms, so I don't want to call it that. But like basically these kind of the blue one and the orange one. So we have this kind of slow incremental system and this fast and flexible system. And we already said that kind of a property of the slow incremental one is that slow and incremental and it's highly retained, and that is like by definition true of in-weights learning in neural networks. The other one is fast and flexible and it's not retained. And that's by definition true of this in context learning. And so what we want to look at is whether these two systems also exhibit the kind of behavioral evidence that has been the behavioral patterns that have been used as evidence in humans. So one study that I'll talk about in a second has shown that when humans are slow, kind of using slow and incremental learning, they show this interleaving advantage, and it dominates in the absence of rule structure. So I'll read these after I give the example, which is better. So this is prior work from this group, No et al., that was looking at this dual learning systems. And here they used this task where they were saying, okay, you have to categorize lines into group one or group two. So like you get some line, you have to guess which side it goes to. This one goes to group one. Okay, guess for this one. Usually I do this interactive, but it's not as fun on Zoom. Okay, this one says goes to group two. This one, group one. And after many examples, maybe people can start to infer what the picture looks like under the hood. In this case, it was like the short ones go to group one, the long ones go to group two, and orientation doesn't seem to matter, or it doesn't really matter for group one or group two. So this is a task that people can learn how to do one example at a time. And what they manipulated in this study was that you can have what we call a rule-based system, which is where it's easy to articulate, or we would call it maybe verbalizable. Like I just said, the short ones are blue and the long ones are orange. That's pretty easy for me to articulate. That follows a pretty clear rule. Whereas I could have this rotated or information integrated condition where the kind of decision boundary cross cuts these verbalizable features. So it's harder for me to describe what makes something blue versus orange in this case, because I would have to say the blue ones are things that are short and rotated not more than a certain amount, or as it gets longer, then it needs to be rotated less, like this kind of weird decision boundary that's actually hard to say. So that doesn't neatly fit this rule-based condition. And then they also manipulated the curriculum that people are given when they're trying to learn this task. So you could either get lots of examples of blue followed by lots of examples of orange, or you can get just a random shuffling of blue and orange all mixed together. And what they found here was that when you have a rule-based structure to the underlying task, people preferred to see the blocked curriculum. And when you had this information integrated that where there's not a clear verbalizable rule, people preferred to see the examples shuffled up. And so this gets used as kind of evidence that there's two systems in play here. There's this slower incremental system, and that's the one that dominates when you're dealing with data that's not following nice rules. And when you're dealing with that system, you prefer the interleaved data. And then in contrast, there's another system that kicks in when you're dealing with rule-like structure, and that system prefers the blocked curriculum, and that's the fast and flexible one. They don't deal with the speed here, but they show this kind of co-occurrence of the rule-like structure and the blocking advantage versus the non-rule-like structure and interleaving advantage. So that's kind of one set of data that we're just in. And then there's a related study that deals with compositional generalization that looks very similar. So this is a project from Decker et al. And they had a similar kind of task where you're given, you're trying to place objects along a grid. And here in this case, it was animals and colors. And so you could either see stuff in a blocked structure where you would see these things one at a time, but it might go down one row and down one, or along one row and down one column. And then you're asked, where does the blue owl go? And in this case, the hope would be that you would guess, I guess, position one, because you're going to say that maybe the columns are organized so that it's one color per column, and then one animal per row. Or you could get the interleaved data, which gives you the same number of data points, and it also covers all the rows and columns on the same level, but it's all shuffled up. And here the hypothesis is it's harder to infer this underlying structure. And what this project found was that when humans were given the blocked structure, they were able to generalize compositionally, whereas when they were given the interleaved structure, they weren't. So you can ignore the kind of interesting part for our purposes is the blue line here in their results. That's just showing that humans did a much better job generalizing compositionally in the blocked condition, and they weren't really able to do it in the interleaved condition. And so this kind of adds to our picture of we have these two systems kind of saying, again, there's like one that dominates when you have rule-like structure. It's fast and flexible. It prefers blocked curriculum and it can compositionally generalize. And then you have the other that kicks in when you don't have that structure. That one is slow. It needs interleaved data. And so this is what we want to say, like maybe in a neural network, the blue stuff is taken over in weights and the orange stuff in context. And so what we're going to do to explore this is we're going to meta train a neural network on tasks that look like this. So here we're using like a large language model, but we're training from scratch. So I guess it's not a large language model. It looks like a language model. It's a transformer language model that gets text as input. So we have a text version of these tasks, but I'm showing kind of a visual one because it's easier for humans to look at, where you basically get a grid of animals and colors, for example, and you're placing a held out animal and color. That's the task that the model needs to do. But if we meta train a neural network to do this over many different grids with different feature combinations and different held out examples, we hope that it learns how to generalize to a new grid in like zero shot in context. So the model will train over many of these grids and its weights will be updated over many grids. And then at test time, it's going to get a single grid that it's never seen before with unseen colors and animals and be asked to place the new object. And that's kind of our measure of the compositional generalization at test time. So that's kind of the recipe is we're meta training the model over many of these tasks and we're testing on a held out task. So we have a variety of results here. So the first is let's first consider a case where we're not meta training the network. So we're just training the model on an individual task itself. This would be like actually doing in weights updates over the new grid. So it's seeing that, the yellow owl is at position, row 1, column 2, and it gets a gradient update based on that. So this is purely in weights learning. And we have two sets of tasks, one that looks like this line task and one that looks like this colored animal task. So they're just two slightly different tasks that have similar flavors. And in this case, we can see that the models, one, they cannot generalize, they can't do in context learning at all. That's expected. They haven't really gotten any signal in order to do it because they've just trained directly on this task. So we have no in context learning at all. Then when you train on a new task, with in weights updates, then you see kind of as expected that the models much prefer interleaved curricula. And this is kind of what we know about neural networks. This is neural networks behaving in their usual way, where if you give them blocked data, they exhibit catastrophic forgetting and they don't learn well. But if you give them shuffled data, they learn okay. So here, this is kind of just substantiating this view of the in-weights learning kind of acting in this blue system that we were describing before, that it's going to prefer the interleaving advantage. But then if we meta-train the model to do in context learning, then we see that the models exhibit a blocking advantage. So here, if you meta-train the network and then you allow it to have weights updates, it's at ceiling. So that's not as interesting. But if you look at the blocked condition here, you can see that that when the model is doing this kind of zero-shot generalization to a new task, it much prefers to see the data blocked versus interleaved. And in the case on the right, especially, that gap is very substantial, right, on this kind of compositional case. So that's consistent with this in context learning acting more like this, this kind of the second system we're talking about. But then I think more importantly is that the in context learning has this property, but it only kicks in when we're dealing with tasks with rule-like structure. So I just showed the results that kind of corresponded to how the model behaves when it gets grids that follow nice rules. So this would be what I was calling the verbalizable rules, meaning like on the task on the left, the short lines are blue and the long lines are red or are orange. And in the task on the right, it means that the grid, like we have nicely defined rows and columns. But we can also rotate this so that breaks that rule-like structure. And in that case, then the in-context learning stops being effective. Actually, the model does a very bad job generalizing when the new problem doesn't match this kind of nicely verbalizable structure. And so once that rule-like structure breaks, the in-context learning performs much less well, and the in-weights learning is preferred, and then the interleaving advantage kicks in again. So there's a lot of like little pieces of results here that I think each one in isolation is interesting, but what's more interesting is kind of this constellation effect of putting them all together because we're trying to understand how these two systems trade off. So kind of summarizing that, human learning sometimes is slow and incremental, sometimes we're fast and flexible. And there's like different behavioral pieces that are associated with these different systems. So some systems dominate when we're dealing with logical tasks, structured compositional tasks with rule-like structure. Those systems are fast and flexible. They generalize compositionally. And then there's other systems that kick in when we're dealing with slow incremental tasks. These are the ones that dominate when we're not dealing with rule-like structure, that kind of a thing. And so we can see that when we have a neural network that's trained so that it can solve some tasks in context, particularly in its activation space, then that kind of provides this unified account where we get this really natural trade-off between which system takes over in which kinds of contexts, and we see the kinds of patterns that we're expecting. So specifically what that means is the neural network is exhibiting this blocking advantage and compositional generalization in exactly the cases that the task itself has rule-like structure. And in those cases, in context learning takes over and shows these blocking advantage and compositional generalization. But when the task doesn't have that kind of structure, then the in context learning fails, the in-weights learning takes over. And in those cases, we see the interleaving advantage and a failure to generalize composition. All right, so that's kind of what I wanted to say about this first piece, which is just kind of like a way of thinking about neural networks where they're not kind of just the traditional way of thinking about neural networks, but have the capability of doing both types of reasoning, but they wouldn't behave just one way all the time, right? The way they behave might depend on the task demands and kind of some interaction with what the model has been trained to do. And so then kind of switching gears a bit, the question is like, this is maybe interesting from a standpoint of understanding neural networks and thinking about the mechanisms. When we're thinking about kind of neural networks as cognitive models, it's relevant to say like we really want to understand these mechanisms if it's the case that neural networks are providing a better fit for the human data than existing models, right? If now kind of thinking as a cognitive scientist, so this is less cognitive science of Gen AI, more just cognitive science of humans. We might ask ourselves whether generative AI right now is going to move the needle on anything we care about in the study of humans. And this is really only the case if there's a chance that they're going to improve over our current best models, right? They need to provide some better fit for the data so that understanding them is actually going to yield useful theories. And I've been excited about the second project because I think until this project, I haven't had a good example of a task where I felt the neural networks were um, could possibly tell us something new that we didn't already know. Um, Unfortunately, I don't have the answer yet for what these things tell us, but again, it's like a pointer that I feel like there might be something useful here. So I want to describe what we've been working on here on a concept learning task with neural network or with large language models and why that might kind of connect to this first project in terms of giving us some new ideas or theories about how humans are solving these kinds of tasks. Okay, so here the task we're interested in is from Steve Pandatosi's work, if people are familiar with that. And this task is especially interesting because it's been used precisely to illustrate like what I would say is kind of the cognitive architecture aspects of humans. So like Bayesian language of thought kinds of models of human cognition. And in this task, it's a kind of a word learning or concept learning task. So humans are given some set of shapes in this case, and they're put boxes around, say these ones are whatsy. And then you're asked to now say which of these ones are whatsy. And it's obviously ambiguous. So some people might think it's triangles. Some people might say it's anything that's yellow or green. Some people might think it's anything with corners. Now maybe you'll get another example that says, okay, now these ones are whatsy. And now which ones are whatsy here? And like hopefully, I mean, again, it's underspecified, but by this, most people conclude that the rule that defines whether something is whatsy is that it's yellow or green, but can be any shape. But of course, there could be other possible rules that explain what this is. And so over the course of many examples, people infer this latent rule and use it to apply. And what they do in this work is they vary the complexity of the rule that is used. So like I said, there's maybe some ambiguity, but maybe we assume that people in this case would infer green or yellow. And this requires some primitives like the concept of the colors yellow and green, as well as this logical operator or. And in Pandatosi's work, they found that if you had this probabilistic language of thought or a PLOT model that basically stored these primitives as explicit representations of things like yellow and green, as well as rules like and or not. And then you learned some Bayesian inference over the likelihood of these different rules and composed them explicitly, you got a very good fit for the human data. So this was showing the correlation between the Bayesian PLOT model and the human responses for various types of rule learning, things like circle or blue, circle and not blue, and increasingly complicated. And so I think at the time that I don't know if they explicitly evaluate a neural network in the original paper, but this is the kind of thing neural networks have traditionally not been very good at because they don't represent these kinds of abstract rules. But what we were looking at was what we are looking at is whether large language models are able to do this task comparably well to the Bayesian PLOT model. So we have text version of the task in order to work with large language models, where you basically just describe that the group is medium blue circle, large green triangle, etc. And then give examples of trues and falses. And the first thing we see is just on an accuracy standpoint. So humans, in terms of how well they are at guessing the underlying rule, are not perfect because some of these are actually quite esoteric for a human to infer. They're like weird, like first order logic rules that aren't super intuitive. So humans are at about 84% accuracy of guessing the intended logical rule. And the large language models that we looked at were basically right in this ballpark. There's obviously some variation, but the best models were exactly on par. And one important thing is they weren't better than the humans, which is the kind of thing you sometimes worry that large language models do. So they're kind of about in the same range um, of how accurate they are. They also show similar patterns in which things they find similar and difficult. So in particular, humans are much better at the propositional logic rules than the first order logic rules. And in many, kind of across the board, across the good models, they show about the same gap in performance between these two categories of rules. What's more important is looking, I guess, like drilling down into this further and not just breaking it by category, but actually trying to track the error, the learning curves of humans. And here we found, so the pre-trained language model, if you just look at the correlation as you see examples and people make guesses, how accurate they are. So you can kind of get a learning trajectory over time. If you look at the correlation between what the language model is doing and what the humans are doing, kind of off the shelf, the pre-trained language model is correlated about 0.5, which is okay, not great. If we fine tune the language model with a small amount of human data, which is comparable to what the Bayesian models are able to use to fit their parameters, then we see this R squared go up to 85 or 0.85, which is actually better than the kind of correlation we're getting from the Bayesian model. And to see what that looks like, you can look at some of these kinds of plots, which is what they use in this original paper. So this is kind of a running accuracy average over the examples that people are getting. So on the first example, you have to guess, and people obviously get better over time as you see more examples. But you can see these pretty characteristic drops in performance over the course of the examples. And these are kind of the types of things where we can see that the tuned language model is actually providing a better fit in terms of magnitude than the Bayesian model at these drops. I mean, both models are doing a surprisingly good job at predicting the location of the drops. But you can see that in these specific cases, the Bayesian model would often overestimate how extreme this drop is going to be, whereas the humans and the LLMs are in a similar magnitude. And I think this is interesting to discuss and interpret. In the original paper on the Bayesian model, the way they interpreted these drops was that this is when the kind of current working hypothesis of the model is invalidated by the next example. So maybe you thought that the rule was green or yellow, but now you get an example where there's some green thing that's not being labeled WUDSY, and you have to like come up with another rule, right? So this is like requires a massive revision of your working hypothesis. And the prior work, Pantitosi et al. Was interpreting these drops and particularly the ability to model the drops as evidence that the Bayesian model had a similar kind of hypothesis, as well as maybe a hypothesis testing procedure to humans, and that's why it was replicating these drops. And so when we see a better fit for the LLMs, it opens questions of whether we should be considering the LLMs as also having a similar kind of a better fit for this kind of human-like hypotheses and testing procedure. We can also see negative examples. There are cases where the LLM has a worse fit than the Bayesian model. And in most of those cases, it typically was that the LLM was just failing to learn the rule at all. So it's kind of a different type of bad fit than the positive example I showed. So just a kind of relevant point of comparison, I think. And we find that when we're looking at this increased correlation, we tend to find that when the LLM gets better, it also is doing it in a more human-like way. So here we're looking at a correlation between the model's accuracy and the R squared with the human responses. And we see a lot of points in this upper right corner, which means that as the model is getting better at predicting the answer, it's also becoming more human-like, when this isn't always the case with the Bayesian model. In the Bayesian model, we have a bigger spread on this like left or right-hand side of the graph, which means there's some more cases where the model is correctly predicting the rule, even when humans wouldn't have been correctly predicting that rule. So there's this kind of general situation here where, at least to me, this is exciting because it says, well, if this LLM is as good or possibly better than the Bayesian model at kind of fitting the human data, then it opens up the question that maybe the mechanism that LLMs are using is a better model of what humans are doing than the Bayesian probabilistic language of thought model that's kind of embodied by this Bayesian model. And of course, we don't know exactly the mechanisms the LM is using, and so that's kind of what we're working on actively. But I think that first project kind of hints at what some of the mechanisms in play might be. Um, but it's at least an exciting position to be in to say, like, maybe we'll learn something interesting here by trying to ask, how does the LLM do this thing, right? Because it could provide a compelling alternative model compared to what we have, or possibly it just re-implements the Bayesian model. I think that would actually be extremely exciting too. And there's maybe some reason to think that it is doing something quite a bit like that. And as kind of a final part of this analysis, it's worth saying that maybe like I said, maybe the LLM is simply just re-implementing what the Bayesian model is doing. I shouldn't say simply, I think that would be a pretty exciting outcome. But there's actually reason to think that maybe it represents a different type of approach to the problem. So we could do this by trying to understand what rule the models are actually using in order to infer what Z means. So on the Bayesian model, we can ask for the maximum a priori or a posteriori rule for the evidence given so far. So that's kind of the mathematical model that is used in order to infer the rule. It like gets I don't want to go as far back in my slides, but it gets a sequence of examples of like the yellow triangles and whatever, and it's entertaining what is the rule that best explains the data I've seen so far in a probabilistic sense. So we can extract that rule from the model. For the LLM, we don't have such a convenient insight into what rule the model is applying because it's just a language model. What we can do, and it sounds a bit ridiculous, is you can just ask the language model, what rule did you use? And I was at first super averse to this because I was like, well, there's all kinds of reasons that this is just kind of bogus, right? Like language models, there's absolutely no guarantee that that the rule they say they use is the rule that they use, or that they even use a rule at all. It might tell you that I thought the rule was not blue, and actually it doesn't even know what that means, right? It's just saying stuff. Like language models really don't lend themselves to any guarantees around this. But my colleague Roman Feynman, who's working on this project with me, convinced me that this was a very interesting thing to study, almost more so because of this, because if it does report a rule that is in fact consistent with what it's doing, then that's even more like warrants even more investigation. So we decided to do this analysis of just asking the language model what rule it used. And we admit that there's no guarantee that this is consistent with the evidence it seems so far or consistent with how it behaves. So we have to independently check whether that is the case. But it's also worth pointing out that the Bayesian model also is not guaranteed to be consistent with the evidence it's seen so far. So, for example, these Bayesian models often have things like a description length penalty or some other reason to discount and sometimes prefer a rule that's not perfectly consistent with the evidence, but otherwise considered better. The Bayesian models are also not guaranteed to have their own behavior be consistent with this rule because it means actually marginalizing over all possible rules. So in both cases, we have like a window into the rule that kind of explains the model's behavior, but it may or may not be consistent with the evidence. So we compute a consistency with the evidence metric. And then it's not necessarily consistent with behavior. So we report those two. And then we can use this as a way to just kind of analyze what are the rules they're using, how consistent are they, and how often do they agree with each other. So kind of on a global metric, these things are actually kind of surprisingly symmetric. So the Bayesian model is consistent with the evidence it's seen. So its map rule is consistent with the evidence seen so far about 96% of the time, whereas the LLM self-reported rule is consistent about 90% of the time. And then the Bayesian model's consistent with its own predictions about 90% of the time, which is actually lower than the LLM, which the rule it says it's using is consistent with its own predictions about 96% of the time. So in both cases, we're actually looking at rules that, at least on the surface, appear to be a pretty good, pretty consistent with what the model is doing behaviorally. But qualitatively, they're often different from each other. So, for example, when the true rule is not circle, you can see that the Bayesian model would produce a rule like not circle, whereas the LLM would use a rule like triangle or rectangle. And in this case, the obviously the Bayesian model is the same, but both of them were perfectly consistent with the evidence seen so far. And this is, I think, very representative if you look at a lot of rules that the LLM really prefers to just join with ands and ors many smaller, more narrowly scoped rules rather than moving over to something like not circle or a more globally quantified kind of a rule. And I think that's maybe consistent with how we might think of LLMs liking to solve problems, but it's interesting to see that bear out. So another example is something like this, where the true rule is circle or blue. The Bayesian model gets it correct. The LLM comes up with an alternative rule that is also consistent with the evidence so far, and in this micro world is truth conditionally the same, but is different, right? Instead of saying circle or blue, it's saying blue or, and then it's like more conservatively scoped yellow or green circle. It's only seen yellow or green circles, and it's not really willing to generalize this to all circles. It's only saying it's a yellow or green circle, right? Again, interesting and something that we're working on testing whether humans actually similarly come up with these more narrow rules, because I think there might be reason to believe that that we would actually take this more narrow read of the data so far. Then you can look at examples where they both come up with a rule that's wrong. So here the true rule circle implies blue, which I always get this kind of wrong, like I get my logic messed up, but I think this is basically like circle if and only if blue, um, or at least just circle blue if and only if circle, something like that. Um, the the PLOT model comes up with not circle, which is about 93% consistent with the evidence, whereas the LLM comes up with a different rule, triangle or rectangle, which is also about 93% consistent with the evidence. So in both cases, they've come up with like a workaround rule. But again, you can see the kind of qualitative differences in how these look. So this is work in progress, and we're still running several follow-up analyses. But summarizing what we've seen so far, I think the concept learning task here that we're looking at has been designed to like show off how humans use logical and compositional reasoning processes, right? Like it's designed to really kind of surface our particular capacity to reason over these logical compositional rules. And so up until recently, I think the best model for explaining human behavior on the task were models that explicitly appealed to those probabilistic and logical and compositional operators, like these probabilistic language of thought models. But now we're seeing that large language models actually seem to fit as well, if not better, on the human data, as well as learning trajectories and error patterns, but seem to show qualitatively different patterns in how they're solving the problem. And I think this is an exciting position to be in, because it suggests that maybe if we can pull out the process that the language models are using, we might have an example of the LLMs actually having arrived at some kind of fundamentally new theory of how humans are doing some interesting process. And that could kind of help spur forward this idea of maybe using LLMs as actual models of cognition in their own right, within domains that are interesting to study. All right. So I think kind of more general discussion spanning both things is, I think something that is generally agreed is that humans' cognition isn't very complex and it's multifaceted, and that modeling the kind of full spectrum of human behavior is going to require many different kinds of learning processes and representational systems. And so this kind of conventional wisdom, or the kind of common approach that I think many of us share, is that neural networks are good at one of these kind of pieces of this puzzle, which is stuff that's like some associative, maybe more semantic, whereas we would need symbolic architectures and symbolic structure for things that are more what we call syntactic, compositional, logical. And there have been examples of these kind of explicit neural symbolic architectures in that way. But what we're seeing right now with current neural networks, like large language models, is that they exhibit behavior that's very different from what neural networks from 30 years ago, or honestly even 10 years ago, exhibited. And so it's kind of calling into question how essential these explicit structural components are. And I think that there's this kind of what was previously a very strawman hypothesis where you might have all of this within a single neural network, kind of warrants revisiting because we at least have to figure out how it is that the large language models are achieving these tasks. And I think there's many things that could come of that. One is we could find that, they're succeeding from hacks, which is still a possibility, although I think increasingly less likely. The other is that they've come up with an implementation of the thing that we were previously building in explicitly. And I think this is a pretty likely, in many cases, likely to be what we find, is that they've kind of relearned something we could have built in ourselves. And in that case, it's really interesting because if that re-implementation differs in even a subtle way, like it could actually open up a lot of really fruitful lines of investigation into like the details of these mechanisms, which could actually be really important for how well they explain cognition. And then there's a third alternative, which is it comes up with a completely different kind of alien solution to the problem. And then that too raises some pretty important questions for cognitive science, I think, about either, whether we should entertain that as a hypothesis of what humans do, or whether we at least need to then investigate why humans didn't converge to that solution, or like what other kinds of things, like it comes a kind of learnability acquisition question. So I think all of this together basically calls for much more work on the kinds of questions that I think probably everyone in this group is already thinking about. Like something I've been very excited about is just work on the mechanisms that LLMs employ. How do we look inside the black box and figure out what they're doing? But also this more kind of hypothesis-driven work on what LLMs are doing. So we can't really answer these questions by just looking at the behaviors of LLMs and saying that they're a good fit for the human data here and a bad fit there, or they, reproduce human judgments on these things and not on these other things. But we have to go kind of deeper inside the representations and mechanisms and try to pull out kind of theories from the LLMs. All right, I think that puts me right at time, so I will stop here. Happy to have a discussion.